conversations about the best way to present something that would be of interest. And you look at the class, and at its core, the class is about the energy transition. And so I thought, okay, what are the most important things that we can get across, obviously culminating in our key interests, which is storage. But when I first thought about how we might sort of introduce this, I said, okay, energy transition, what does that really mean? When you think about our grid that we operate with, it really has a very defined starting point in 1882 when Edison switched on the Pearl Street Station. And that was where we started the paradigm of centralized generation, distribution, transmission. And that paradigm really didn't change that much for 100 years. Obviously, huge expansion of the grid, but really that basic notion of how we're going to do this didn't change a heck of a lot from 1882 to around 1992. And then I think, well, what are the factors that may have disrupted this century-old paradigm? And the only thing I can really think about is that's when I entered the practice of energy management. So I think that probably, I don't know, correlation, causation, I'm not 100% sure, but I will say that I started practicing in this area. I'm a lawyer by trade. I started practicing in the area in 1992. And the reason I want to just mention that, first of all, we were supposed to introduce ourselves, but I think it's actually also somewhat relevant, and any questions that you might have, if you think about from 92 to the present, and certainly projected absolutely into the future, the energy system has gone through a complete revolution, and that's a revolution that we are virtually still just at the beginning of. And I think that the energy revolution is inextricably linked to the major environmental issue of our time, which is climate change. They're linked for all kinds of reasons, of which I'm sure you're well aware, but the energy sector accounts for a vast proportion of the greenhouse gases that are causing climate change. And the measures that are being used to address climate change have enormous impacts on our energy system. So 92, a lot of change. So what's happened then? 92, we got the UNFCCC, our one global treaty to address climate change, okay? I started practicing law then in New York City and represented major utilities, Con Edison, PSEG, really seeing how they're starting to deal with that. The other major thing that started to happen in the 90s that, it's funny, Hal and I were sort of talking about, there's so much going on with energy right now. You almost forget the 90s deregulation. That was a massive paradigm shift in how we operate these vertically integrated companies to deliver energy. And again, I represented PSEG through that. And Hal brought up a name that I haven't heard in a long time, Enron. So, but that, I can't tell you how disruptive all of that was. And Enron, that's the poster child, but it happened in every state in a different way, but it really fundamentally changed how we think about the delivery of energy. Then you kind of progress through the 90s. You get the Kyoto Protocol in 97. And then you start to get to the 2000s, and a lot of things start really heating up. Me personally at this point, I was still practicing law at that time, but sort of seeing all of this develop. And then 2001, George W. Bush pulls us out of the Kyoto Protocol before it went into effect. And there again, that was just a massive impact throughout the climate and the energy world. Since 97, when the Kyoto Protocol was agreed to, until 2001, the assumption was that we really were going to look at a global approach to this, to changing the energy sector, to trading protocols and mechanisms. And all of a sudden, the largest emitter pulls out. And that ushered in what we lived through the entire 2000s, which was the divided world of Kyoto, non-Kyoto. Now, around this time, I went into government for a little bit, and then I came out in 2004 and became Chief Sustainability Officer at Honeywell, which at the time was the largest manufacturing company in the world. This kind of, I love it to death, but this huge bloviating, I think is the word, 19th century manufacturing, 300 manufacturing sites, massive emissions. And they, the CEO at the time and the board did say, listen, this is not how we're going to start looking into the future. We need to get in here and start doing something about it. So they brought me in and we set up the sustainability organization. There weren't really very many at the time, particularly in large manufacturing companies. And I will say, and happy to talk about this, how sort of things be fun to talk about this, but I don't think there's enough time. We did get in there and we came up with a strategy that resulted in over 7,000 projects being done. And by the time I left, we had decarbonized by about 95%. Why do I say that? First of all, a lot of different types of technologies went into that. It is not just about the formulas. There's a lot of people that had to do all of that. So a lot of behavioral psychology went into getting to that point. But at the end of the day, it does show you, and I often say, by the way, we did not do that with technology from the future. We did that with existing technology. And now pretty much, Honeywell's pretty much at zero, scopes 1 and 2. We can get into all of that if you want to. But so 2001, Bush pulls out of the Kyoto Protocol. Massive, sets up the Kyoto, non-Kyoto world. The other thing that it did, and I actually wrote a book on this that came out in 2019, because I think it's fascinating. One of the things that did is the civil society, the NGO world, was so invested in Kyoto. They spent so many resources. They were right there in the negotiations. And when they saw that the political world could pull the plug on that with the flick of a switch, in my mind, that revolutionized how NGOs viewed their relationship to government and to environmental issues generally. And that is when you can absolutely track the formation of an entire civil, non-governmental regime around managing climate, to the point there where when I was CSO at Honeywell, we categorized our greenhouse gases based on an NGO protocol. We reported them based on an NGO protocol. We set targets based on an NGO protocol. We faced consequences of making or not making those targets based on NGO surveillance. So it's kind of fascinating from a governmental perspective that when you saw this kind of massive failure on the governmental sector, civil society created essentially a shadow government for climate. I've always found that really fascinating. Probably no one else does, but that's what drove us. And I will say that, I sort of hit the sweet spot. I came in, became CSO in 2004, was there until 2023, and you saw this tremendous, and when you think about what makes things change, by tying it to climate, you all of a sudden had shareholder pressure for change, which ultimately is what drives corporate behavior. Why is corporate behavior? It's because they are the Willie Suttons of the climate world. That's where the emissions are. Okay, so I'm going to wrap this up pretty quick. You kind of get to the end of the thousands. excuse me, the 2020s or the 2010s, and you start seeing a couple things again. You do see this backlash against wokeness and ESG, and that immediately filters into climate. You see that our new president has again withdrawn us from the Paris Agreement, so that's a whole dynamic. But the other thing that's been introduced is beyond climate. I think it's fair to say that there is now a widespread and very significant recognition that 1882 paradigm is not adequate for our system going further. The American Society of Civil Engineers gives our grid a C- overall. NERC just came out with a report that said the US is in several markets is going to face significant difficulties over the next 3 years meeting energy supply. And with all of that, that'd be bad enough if it was status quo. This is then facing a massive increase in demand, which we have not seen in decades. And the demand is coming from electrification of transportation, electrification of heat, onshoring is a massive part of it. Everyone talks about data centers, AI. This was a kind of a steady state even going down. You know, back when I was in law school, everyone was saying, you know, we're going to lick the problem of pollution from utilities through energy efficiency. Now, all of a sudden, we're facing a world where demand is ballooning, and we've got a C- grid. And so now, so much of the thought is like, okay, I've seen estimates of 21 trillion to rebuild our grid to support the energy transition. That's a lot of money. And so now we're thinking about what are some smarter ways. And that's a big part of where storage comes in. So I'm going to hand it over to Hal.
Thanks, Evan. So a lot of themes there. You know, one thing I want to flag on Evan, he was really one of the OGs as a CSO for a big global, and I've been in energy management pretty much my whole career, and I've not met anyone who has a number like 95% savings. So really just massive and on a global scale. Let's see. I guess I want to start with, you're all in the right place at the right time, being in this room, thinking about this issue and learning about it. There's massive opportunity out there. There's massive growth. There's massive inadequacy in the infrastructure, as Evan was highlighting. But even the way grids operate and the way we as energy consumers act and purchase electricity is based on this very limited view of 15-minute interval data, right? Like corporates pay demand charges, but there's no granularity to it. When you look at your utility bill, it gives you your total consumption for the month, and it gives you one moment, highest consecutive 15 minutes of grid draw. That is garbage. It's complete garbage. And what do we know about peaks mathematically? If you're going up, this is the highest moment, it's going to average down over those minutes. I don't know how much higher the amplitude on that peak was than what I'm reported on my bill. And you know what else? The utility doesn't know either. Why don't we have better granularity? It's tough to invest in something like metering. What's the return on that? How do you rate base it? How do you convince thousands or hundreds of thousands of people that this is a value while they're still going to pay the net same or similar on their energy bill? So there are a lot of fundamental challenges. But you know what I would say is, as engineers, you're the ones who can see it, you can talk about it, you can understand it, and you can make it approachable, not just for individuals and decision makers at building level or customer level, but for utilities themselves. They've had blinders on. The organizations are so siloed. This is like a weekly conversation with different people. It's tough out there, but there's so much opportunity. There's room for new ideas. There's room for massive innovation. And I guarantee everybody in this room can come up with at least 5 that would massively change the market. All right. So let's see. Let's poll the room. So obviously we're studying here. What's next? Who's going to grad school or going to continue with schooling? Show of hands. Okay. Who's planning to go workforce? Okay. Who of those is planning to go into the energy industry? All right, that looks like a close number, so that's good. That's good retention. And then majors, so electrical engineers. Okay, mechanical. Chemi. Math Sci. Civil. Missed anybody? Shout it out.
Environmental.
Environmental. Good one. Same. Okay, cool. All right, so I'm a mechanical engineer. So I started out designing complex buildings, hospitals, laboratories, pharma, did a lot of consulting for universities. In terms of climate, does anybody know what the biggest carbon footprint is globally? Like the end use cause? Shout it out. No guesses?
Meat industry?
What's that?
The meat industry?
The meat industry, that's big, especially with raising, but it's not the biggest.
Transportation.
Transportation's big, not the biggest. I'll give you a hint, mechanical engineers. Generation, also not quite the biggest, although depending on how you count scope 3, I guess, it would be. It's buildings. So buildings account for 39 or 40% of global emissions. 12% of that is embodied emissions. So what goes into actually manufacturing the materials buildings are made of, construction, all the logistics involved with standing up a building. The other 27, 28% are operational emissions. If you kind of whittle that down from there, what's the largest use in a building?
Heating.
Heat, electricity. But what's the end use? Heat's a good answer.
Lights. Air, heat and cooling.
Heating and cooling for sure.
Heating and cooling. It's HVAC. That's right.
Where you live too.
Depends on where you live, highly variable, seasonal differences, but roughly, depending on the building type, like, I don't know, 40 to in industrials or healthcare or laboratory could be 75%. Biggest component of heating is fan energy. If you're a mechanical engineer at a design firm, nobody cares about fan energy. Nobody looks at it. The way that we design ductwork and fan systems, and even the way the OEMs innovate in fan technology, similar to the status and design of the electric grid, is based on the initial tech. No one reworks this stuff. It's not sexy. It's not exciting. So if you are a mechanical engineer and you go into design, and I'm positive there are parallels with every field of engineering, don't let things slip through your fingers that can be opportunities that matter to your clients or your organization. It's you guys looking for these opportunities and, kind of not leaving any BTU or KWH behind that will transcend to kind of where we all need to get better practices as an industry and better outcomes. And so I'm going to jump on Evan's coattails for a second. So, the grid that was initially designed, the concept of it in the 1880s, 1890s, was mostly built out post-World War II. So that equipment now is 70, 80 years old, right? Massive. Many, 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 many miles of it. I wish I knew the number. But that equipment, not only was designed for a paradigm that is changing now and has been changing for a while. I mean, the way we use electricity, the needs that we have. I don't see a lot of outlets in this room, but some of your classrooms have outlets where you can plug in wherever you're sitting, right? Like how many classrooms had that 20 years ago? People weren't bringing laptops to classes 20 years ago. So, these shifts are happening constantly. That equipment and that structure was intended to last for 50 years, but does anyone genuinely think we went back and replaced it? Nope, deferred maintenance. We can't rate base this. We can't refinance the $21 trillion worth. So we're in this period where we know the biggest machine in the world, which I believe is the US electric grid, is massively inefficient, right? So every year I look forward to US Department of Energy releasing their Sankey diagram. Does everybody know what a Sankey is? Okay, this is worth Googling, especially if you're on a laptop right now. But look up DOE's Sankey diagram for 2023. And it shows you, on the left side, these are all of, I guess, the sources of generation. Full mix, right? You've got coal, diesel, solar, wind. And on the right side, you go to end uses. So you have buildings, transportation, industrials, all of those things. But then you see the losses. I think it's like 69% losses. Does anybody have it up? Can you tell me how much is waste heat in that system?
61.5.
61.5%. 61.5%. So if we were grading them, that would be like a very deep flunking, right? The reality is there are losses in transmission. There are losses when you have a combustion process at a source that's centralized that has no use for that waste heat. There's not a customer there waiting to take off heat from a generating plant. And so we're just built in this paradigm of it doesn't really make sense for what we're doing anymore. And frankly, the problems that it's created and creating for the world. And of course, this puts many on Earth at significant disadvantage. So as Evan mentioned, we're in this massive period of grid transition. Part of the problem, well, a big part of the problem is utilities. But part of the problem is that all of the people who've spent their careers working and working well, in this industry have never been in a period of grid growth. It's not happened. Simple things like developing more efficient lighting, VFDs, the ability to kind of ramp loads, modular builds within HVAC equipment, more efficient operating curves. Kind of the idea of starting to care about how efficient systems are and components are wasn't really injected until the early 90s or late 80s. And so generationally, or maybe that's a bad word for it, but every few years you kind of get better, but you reach theoretical limits pretty quickly. And so you either need to find paradigm shifts within each of those end uses, or you're kind of stuck with what's there. So, again, massive, massive opportunity. Thinking about the grid as a whole, we're really dealing with massive central generators. I think about this like a tree. And you're feeding it out to all of the leaves at the end. Massive, massive tree. The opportunity that's before us, where land becomes the resource for what needs to be our new source of generation, mostly wind and solar, but there are other options and other flavors there that are good. It's really feeding backwards, leaves to trunk. So instead of having few massive centralized generators, you're going to the opposite. You're going to many decentralized generators. The opportunity there is you can cut out transmission. You can solve this without wires, which, by the way, saves a massive amount of costs. It increases resiliency at the ends. It enhances decarbonization. And it's kind of like the best flavor that's ever existed for the grids. Microgrids are phenomenal. I mean, it's massive, massive growth is in the sector of renewables, and I know that's the most obvious thing. But with this, we need to really rethink how we're doing it, the whole system level, and making sure we do it in the right way. Now, we still have to solve for a lot of this aged infrastructure, right? The $21 trillion. It's not going to go away. So we can't fully kind of divorce from utilities and their antiquated, challenging business models to make it happen. So I'm going to spend a little bit of time talking about utilities, the way they think about it, the problems that they're facing, and then eventually we'll get to kind of the whole point of us being here, which is batteries and safe batteries at that. All right, so grid growth. Evan mentioned them. Why is the grid growing right now? Increase in demand. What are the demands coming from? Electrification of transportation. Who's got another? Yeah.
Yeah.
AI data center. Okay, that was yours. Two more, maybe three. What about another kind of electrification?
Heat for transportation.
Heat. Okay. And one more. Think big industrial, manufacturer, economic growth. Bringing manufacturing back to the United States is a theme. Sorry?
You got hand in the middle.
Oh, I'm sorry. Yes. Something is happening under there. What?
You mentioned onshoring.
Onshoring. Yes, onshoring. And then the last I would say is kind of like, you know, right, there aren't outlets at every one of your seats, and facilities folks, I'm not suggesting that. But right, what are we going to be doing differently in 5 years where we're needing more tech, you know, as we use it in our individual day-to-day lives or in our work environments? So there's also this kind of, I think, organic growth that we don't foresee yet of how we're going to need more energy at the leaves in that analogy. Boy, I am massively not on time here. All right, so we'll talk about utilities really quickly. So generation curves of fossil and of nuclear. If you need more, you burn more. It's stable, right? Generally. Problem with renewables, let's start with solar, right? Very predictable. Goes like this. In a lot of places, right? This is kind of what buildings do too. So that's not bad. It's pretty good for on-site buildings.
Ithaca.
Not in Ithaca. Yeah. Well, you know, winter time. So if this is peak summer, this is your winter in Ithaca. It probably peaks at a third of what your summer peak is. And beyond that, some days
Bullshit.
you got nothing. Your panels are covered in snow. So it's a big problem with how you manage this. And if you think about electrification of heat, which on a building by building level, you know, depending on the severity of your environment, might be a 4x expansion in your building's need for electricity at peak, we shift our grids from being summer peaking to winter peaking. So if solar is the way to go, which, you know, it pretty much is, then especially at the leaves, you kind of have this period where you're going to need electricity the most. So are all of your neighbors, if you're in a cold climate, you're going to have the worst production. And by the way, it's been snowing for a week. Does the grid collapse? What do we do? People die when it gets cold. You have to have something. And so in a way, batteries are part of that. In a way, I think that's going to be a reason why it's difficult to fully divorce from fossil. You might need some for backup. Certainly in the medium term, we would. But, you know, hydropower looks really good. Nuclear looks really good. But a lot of the protocols that Evan mentioned, which are great and have great support and following, sometimes they don't, like they're not solving for zero carbon. They're solving for it needs to be renewable. And in some definitions, nuclear is not renewable and even hydropower is not renewable. That offends me. So you all, you know, search your hearts for how you feel about it. All right. I think I'll talk utility markets next. So deregulation, is that a word folks have heard of before today? You guys looked at this? Yeah. So it's the kind of ability to shop around and pick who your electricity seller is or your gas seller. So Enron came up with this. They really abused the system in California so that they could make more money. It didn't go well. But now many states and groups of states have deregulation. So generally speaking, you're either in a part of the country that is deregulated, where you get to pick who your provider is. You don't have a choice if you're in a regulated territory where there's one utility, or it's kind of regulated, but kind of not. You could live in a municipal area where the city has their own utility, maybe their own generation or agreement to get it, or here on campus, right? Cornell operates their own grid, which is different costs involved in all of these models if you're a customer, different exposures, different abilities to play into markets. what Professor Hanrath mentioned before, you know, I love the change in energy. That's exactly what I think about. You know, there are moments where the time scale that you're playing in matters. You can only do most of those things in a deregulated market. So frequency response, where you use a battery to clean the power, can last for minutes, seconds. It's typically not a long time. What's really common is a grid service called demand response, where the utility says, we're ramping up, it's the hottest day of the year, we're gonna need more cooling because it's still getting hotter and everybody's about to go home and turn on their air conditioning. What do? Well, we can either turn on a fossil fuel peaker plant. That's a super expensive asset, not only because it needs to respond quickly and kind of be in the right place from a grid infrastructure perspective, but also because these units are designed to be peaker plants. So you only run them on the hottest days of the year. So you look at all that capital invested, all the operating costs to manage those, just so that they're ready to run for 16 or 20 hours a year, 4 or 5 days of the year. And so they end up being massively expensive, and they also end up being the dirtiest components of the grid. Because within that, you have the entire grid mix of everything else. Everybody who's building solar, all of the wind is contributing at those moments, typically. And so a phenomenal way to decarbonize, lower costs, benefit everybody, including the utilities, is demand response. This was really the first grid service to emerge. So typically you get a call from the utility, and they say, tomorrow between 2 and 6, we're gonna have a big problem. We're gonna need you to reduce load. So the owner of the building gets paid to reduce load. So these kind of interactive agreements are starting to emerge. They're not yet available everywhere, and they always depend somewhat on local regulation, resource mix, but also on the building's ability to curtail themselves. Now, that's good. This is where I'm supposed to transition to batteries. Batteries change this, right? Why do batteries change this? Instead of turning off the air conditioning on the hottest day of the year, what do?
Battery.
Pull from the battery. And my favorite thing about batteries is, does anybody remember what we said about percentage of a building's load being HVAC, roughly? I said like 40 to 75% depending, right? Instead of marginally shaving some of that HVAC load, and for a university, right, if it's a hot day and there are classes happening, you're still required to ventilate that building. Maybe you can dial your fans down a tiny bit, but you're going to keep them running. So you're not getting a full erasure of that load in those moments. You're getting a marginal one. So you can turn off cooling. You can let your set point in every classroom rise by 2 or 4 degrees. People don't love that. Administration doesn't love that. So it's a sacrifice. Or you could use a battery to island the entire HVAC system, that whole load. Or you could use your battery to island the whole building. Or you could use your battery to island the whole building and export and provide benefit to your neighbors who don't have batteries. Why has this been tough to approach? Why hasn't this happened more and everywhere? Let me put it differently. What's wrong with batteries? Yeah.
They don't work as well in cold climates.
Don't work as well in cold climates. Not true of all batteries, but it's a good point. Yeah.
Energy density.
Energy density. Energy density. Tell me more.
You need large spaces.
You need a lot of space. And in buildings, you know, right? We use the space. We built it to use the space. We don't build it to house equipment, or at least not just. So that's good. Yeah.
They use materials that you have to mine.
Yeah, right. So if you think about the embodied carbon of investing in batteries in the supply chain, highly relevant to, you know, the whole picture impact on climate change. Yeah.
Sorry, I'm not an engineer, so this is more of a question, but when you're charging those batteries up and they heat, do you have to have a cooling system for the batteries?
Sometimes. But go there. Let's say you need a cooling system, but you don't have one. What happens? Yeah.
Fires and safety risks.
Fires and?
Safety risk.
Yeah, massive safety risk. So what are most batteries in the world manufactured for today? They go fast. Transportation, cell phones, a lot for consumer electronics, and that's certainly been growing. But most are for EVs. So you have these global massive supply chains and growth, and with massive growth in them, and some of the largest companies in the world who are investing in this tech. And then you're saying, love the EVs, keep them going, electrify transport, but it's tough to kind of intercept a paradigm and change what you're using it for, right? Like there's a parallel with our grid is inadequate to these batteries were developed for transportation, but we want to use them in buildings. Does anybody know how many, has anyone heard of thermal runaway? Yeah? Can you tell me about it?
Between,
Sorry, a little louder.
like, the event where there's a shorting between.
Yeah. So there's a short and it creates a fire. But you know, the good thing about car batteries is they're energy dense. The bad thing about car batteries is they're energy dense, right? So when this does happen, it's a massive fire. It's an explosion. It's catastrophic. Does anybody know how many Teslas statistically have the risk, not through any kind of car crash, but of going into thermal runaway? 1 in 46,000. Think about that if that were homes. Think about that if you're in New York City or if you're in a high rise anywhere and every apartment has one so that they can island or the whole building has a massive system. In a car, if that happens, you get out of the car. If it happens when you're not in the car, the fire department pulls the car away from a structure or away from people. It happens in a building, unacceptable. The safety implications of this and of utilizing the way that we typically, and the only way at scale that we've built batteries is entirely inadequate for the need of decarbonizing the grid. And so that's why Evan and myself find ourselves working at a startup battery company, which I think, you know, neither of us would have guessed we would be doing at the beginning of our careers. So Viridi figured out a way not to solve for thermal runaway, because that's a native risk with lithium ion chemistry and a lot of other chemistries. But they came up with a way, our founder, to isolate thermal runaway when it may happen, because it's a statistical inevitability. So we figured out a way to capture it and prevent that propagation. So let me go into that a little bit, and then I'm going to try to really stop because I really want to hear some questions. This is the cell that we use. This is lithium ion, NMC, nickel manganese cobalt chemistry. It's one of the most common cells in the world. All tier 1 manufacturers make this. This used to be used in Tesla cars, largely considered automotive grade. We picked it because it's stable, made by tier 1, available, and that's what we built our tech around. So cell, module, and then we have 270 of these modules go into a pack, which is roughly the size of a large suitcase and 1,200 pounds. So what we do is we provide a few levels of isolation. When thermal runaway happens, there are 3 things that you have to solve for. The cells themselves kind of go off like a grenade. So the cell wall, which of course is metal, pierces the neighbor or many of the neighbors, automatically triggering them to go into thermal runaway. Because when a cell goes with this chemistry, it's at 600 degrees C. So what we did is we took phenolic plates, just a plastic, that can absorb whatever the shrapnel is that might come out, and it gets embedded in here. So you're no longer worried about that outburst. Second thing that happens is, kind of just said it, 600 degrees C. And these are, I don't know, 4 millimeters apart. You're worried about setting off your neighbor from that energy outburst or the heat outburst from the cell when it initially triggers. So we've got these large catch-up packets or sad Capri Suns that are filled with a fluid that was developed for rover when it went to Mars. So we co-developed these specifically for this application. And within here is a carbon fiber wick, some phase change material, and some distilled water. Heat rapidly triggers this, it opens and immediately extinguishes the cell. And so in the build of the pack, you have these surrounding and the phenolics surrounding every dimension of every cell of every module. The third thing we had to solve for, which academically for me would have been a nightmare, is dissipating the pressure wave that comes off when that explodes. So all my mechanical engineers, right amount of spacing, you can dissipate a pressure wave. So it is a geometry problem. Those three things, and batteries become safe. So we've gone through UL, we've gone through CSA, I don't actually know what that stands for. But
CSA SP 1000 standard, the eSafe standard for UL listing, the 9548 testing. We can go over more of this in the question section, but
all the stuff.
everything we have said, it's been through for it.
Yep. All right, so last piece, I should have said this earlier. What do batteries do for decarbonization of the grid as a whole? Yeah,
Allow more renewables to come onto the grid.
more renewables, why?
Because now we can kind of safeguard against the intermittency of them.
Right. And so what we're talking about, of course, is load shift. It's great that it's producing on my house at noon. I'm not at my house at noon, right? I'm going to save this for nighttime. Professor Hanrath mentioned this. Sometimes you need long duration. Sometimes you need to save that for winter when you have it in the summer, right? So different needs, but load shift of renewables is huge. What else? We covered a few, right? Avoiding use of heat peaker plants, interacting with the grid in a positive manner where everybody kind of wins and can, utility gets cost saving or generator gets cost savings. We get resiliency, we get decarb. Most batteries that have gone out there, somewhat because of safety limitations of putting them at the leaves instead of at the trunk, but also because utilities are good and they like to build big projects, right? Most of the batteries that are out there are grid scale. I mean, megawatt, hundreds of megawatts, gigawatts starting to happen. And nonetheless, safety is an issue there. So this is one of the safest cells on the market, which we use, of course, in our base tech. It has a published risk by the manufacturer of 1 in 40 million of these going into thermal runaway natively, not because of mistreatment or any kind of collision or anything like that in its lifetime. That's a few hundred megawatts. Moss Landing in Monterey, California, was the largest grid scale battery plant in the US. I guess it technically still is. It just caught on fire for the 4th time 2 weeks ago. When these go, Evan, what are the fumes that come off of this?
HF, hydrogen fluoride, is the big one.
Yeah.
Yeah.
Right? Like the surrounding towns are told, don't be outside, close your windows for an unknown amount of time. Like massively toxic. So even at grid scale, the opportunity is there to bring in safety, to do it, in a manner that reduces risk from utilities and insurance companies and contractors that build them in underwriting, ultimately would lower the cost for them. But even the insurance markets are slow to recognize this as a real risk. But this is where we need to go. The suggestion here isn't that Viridi is the only solution, but it's really like we need to pivot and actually scale this market in a way that doesn't compromise everything we're trying to solve for. All right. Now I think let's pivot to some questions. Please come back.
I'm just kind of wondering, seeing as like you developed the technology to kind of prevent thermal runaway,
Mhm.
have you ever thought about like implementing it into companies who make EVs and that kind of thing, like how would that work? Like testing?
Yeah. So one of the ways that we extend cell life and limit the likelihood of thermal runaway occurring through how we treat the battery is we limit its charge and discharge rate. So, and I didn't know this before I came to a battery company, but 0.2C. So that means that we discharge at 20% of the total capacity. So for a 50 kilowatt hour battery, we would charge and discharge no higher than 10 kW. A car where you're going from, not moving at a stoplight to a Tesla, what is it, insane mode, or I think there's an upgrade to that, right? Yeah, right, like that, I don't know what the C rate is, but it's way over 1. I mean, maybe it's 20, maybe it's 50, but so that for that reason, our technology and approach to this won't work in a car.
You think weight
Yeah.
or,
Yeah, it's also heavier.
weight? But you got phenolic plates in there, you've got the pouches of the cooler material. So anyway,
Yeah.
it's probably not.
We're talking about this enabling microgrids
Mhm.
and you have more of those. How would it be a bigger issue trying to keep those all connected so they could all contribute like power, same phase, voltage, et cetera, if it's not coming from the central plant?
Yes,
Maybe you should talk about the connectivity, your team,
yeah.
because that's important.
Yeah, so you can set up inverters to be grid forming or grid following. So if the grid exists, if power, is flowing, whether or not you're drawing from it through your meter, you can follow that waveform. So you're thinking about it in completely the right way. If you had your, call it campus, up and running and the grid feeding it was down and then it comes back up, you then have to figure out how you pivot to follow that waveform. Yeah. So-
Power runs was incredibly sophisticated team at Viridi that's probably the most sophisticated IoT, AI related connectivity. And all of those things where you have to know exactly what the grid, the load, the battery is doing. It's facilitated by the electronics, which
Yeah.
is a 50-50 part of where we are.
Yeah, absolutely. And it's, we wish we had more time. But like that's a big part of it because it's not just, do you have a battery? It's, does the battery do what I want when I need it to? Does the battery enable opportunities to pay for itself? The 4 common grid services that are available right now are not available everywhere, but they will be. And by the way, the incentives for each of these, the payouts, where they're available, and the number of grid services will be more in 5 years than they are now, and they will be much more in 15 years. So there's this need to be future-proof, to be future-ready, and to be nimble to say, now in our hierarchy of decision-making, because the cost for spinning reserve went up, we want to prioritize that above demand response. Or in this mode, now we think about it differently. You have a question?
You commented about this a little bit in the first response, but at the high level, apart from the charging rates that you mentioned about and discharge rates, are there other differences between in your isolation strategy between your battery packs and say Tesla battery packs? That's sort of the 2 parts. So
Yep.
this part, and then if so, do you think a combination of your battery packs with something like, let's say, a supercapacitor to integrate the high demand points would be beneficial? Or
Yeah. So first part's easier for me to answer. So I would say weight, which Evan mentioned, definitely. The other main difference is that car EV batteries typically have cooling, active cooling, and liquid cooling. So if you imagine 270 of these stuck into a suitcase, like and crammed in, you would probably think about, you have channels of very cold water going in between every 2. And so much more sophisticated in that way. I think potentially on your second question. Yeah.
And when you say Tesla, are you talking mobile or stationary? Because, Tesla also does generally large scale. They're very large or very small, and we're kind of in the middle. And I guess it is important that this technology, no one else has it because our team developed it. I think the PhD out of MIT, a fabulous guy, and that's why that is different. No one else has that, so.
What's the cost?
I love that question. So, we do come at a premium, not a magically high premium, not a super high, about $650 per kilowatt hour.
So what proportion of a module is the cells as opposed to the protection?
A decent amount of materials go into the protection, and we also build our pack at a 1/4-inch steel, like it's really, really hardy. I think it's 55% of the cost or maybe between 40 and 55. Non-trivial, yeah.
What's the target audience of this? Is it individual households? Is it communities, utility scale?
Yeah, thank you for that question. I think about that a lot. You know, if I think about my own career and what I've observed, the most challenging thing with technologies is adoption, and the most challenging market to motivate is an individual homeowner or household or person. And so from that perspective, the greatest opportunity is for homes. You know, I think we like the idea of corporates and real estate behind the meter where our safety feature is valued. At grid scale, I think we will also play a part there. Safety needs to be more important. But you know, the reality of utility decision-making, there are 5 things that matter: cost, and safety, in that order. So
And I think it's also the good thing to know, because I think it's the battery, you know, the system generally is we do stationary and we do mobile. And those are very different when you think about, you know, stationary. I have a building, I want to put it there to do all those things, the response to the, you know, the load shifting, the response to the, all of that, and that's got its own dynamic. But then we also make them mobile that are fitted, and that's when you say, like, we just powered Burning Man Festival, which you couldn't do. We saved them 100,000 gallons of diesel fuel, you know, and that whole dynamic of like being able to take power and move it wherever you need, like, hey, we want to do EV charging here now. And so we can move stuff there. So that's, I think, something else. So those are kind of the 2 big categories of the stationary and the mobile.
Yeah.
Gives us some scope, so.
All right, join me in thanking Hal and Evan again. FYI, there's, aside from these samples here, I think you guys brought
We have a unit with us.
a larger system outside, so you can look at that. And then there's also, excuse me, there's lunch in Poland 128. I think if you're interested in food and have further questions for them and then further discussion after.
and look at our job board for jobs and internships.
Oh, sorry. Yeah, absolutely. Perfect. Thank you so much.
Hey, thank you.
I would have done a longer, sorry, but I've only been much talk about how. There's a carbon.
Well, not just but he's upset.
I can kind of feel that. So it's.
That just makes
Activate it, so it'll absorb all